Sorting is the problem of arranging things in a specific order. And QuickSort is the fastest sorting algorithm there is in practice. Today, we are going to learn QuickSort algorithm in 3 basic steps, starting from the simple concept of a rank. So, let's get started. The rank of an element is the position of that element in the sorted list. Or, more importantly for us today, it's the number of smaller elements plus 1. So for example, in this list A, the rank of 5 is 3 because there are 2 elements smaller than 5. The rank of 1 is 2 because there is only 1 element smaller than 1. Similarly, the rank of 10 is 5. Sorting and ranks are directly linked to each other because if you give me the ranks of all elements in a list, I can give you the sorted list by just placing each element at its rank, as you can see here. Let's take a note of this observation that ranks can be used to solve sorting. The second fact about ranks is that they are rather easy to compute. Well, all you need to do is compare your element with every other element in the list, keep a track of which elements are smaller and which are bigger than our element. The rank is then going to be the count of smaller elements plus 1. Here is a straightforward algorithm to compute the rank of an element. We keep the elements smaller than P in S and bigger than P in another list B, and the rank is just the length of S plus 1. Some of you clever folks might be thinking that this rank algorithm is probably longer than it should be. Indeed, there is a smaller version of rank algorithm. But let's not worry about it at this point and go with what we have on the screen. Well, what do we know so far? We know that the rank is easy to compute, and we know that if we know the ranks, we can do the sorting. These 2 simple observations give us our first QuickSort algorithm. In this simple first algorithm, we compute the rank of every P in our list and then store it at its rank's position in a new list. That's going to be our sorted list. In the next part, we'll improve upon this rather crude version of QuickSort algorithm into a more refined one. Let's have a look at how we are performing sorting on our favorite list to see if there is something we can improve on. Remember, our goal is to reduce the number of comparisons. Well, we compute the rank of 5, keep smaller elements in S and larger elements in B, and that gives us the rank or the position of 5 in the sorted list. Here is a simple but very crucial fact about the elements in S and B. The rank of every element in S is smaller than the rank of every element in B. This is simple because we know that we have compared all of these elements with 5. If 1 is smaller than 5 and 10 is larger than 5, then 1 must come before 10 in the sorted list. But it's also crucial because now we don't need to compare these elements with each other. We still don't know the relative order of elements in S, but we do know that all of them are going to be to the left of 5 in the sorted list. and the element in B are going to be to the right of 5 in the sorted list. But how does that help us? Well, it helps us because now we can treat these two lists as two separate sorting problems. We are never going to have to compare an element in S with an element in B. Let us write this down in our modified QuickSort algorithm. So now, instead of looping over all elements, we are just going to call our own QuickSort algorithm on S recursively. Similarly, we are going to make another recursive call on B as well. And the results are concatenated in the final sorted list. But we do need to take care of one more thing, which is that we need to add a stopping condition. Whenever you write a recursive algorithm, you must provide a stopping condition. In our case, this is quite simple. Whenever A contains 1 or 0 elements, there is absolutely nothing to sort, so we can just return A. This concludes our second version of the QuickSort algorithm. Let us do a complete run of this algorithm on our list. Okay, so here is our QuickSort algorithm so far. And the question we are going to worry about now is that do I really need to allocate separate space for S and B to keep smaller and larger elements? Or is there a way to keep them somewhere else? Well, we can keep this list within our original list A. We are going to keep two counters, I and j, which can be anywhere between 0 and the length of A. Everything to the left of I is going to be S, and everything to the right of j is going to be B. Before we start our sorting algorithm, S and B are both empty, which means that I must be -1 and j must be the length of A, which is 5 in our case. We start with the first element. Note that the first element is going to be I plus 1 in this case. So I plus 1 is 0, and at index 0 we have 5. We compare 5 with the element at the next index. In this case 1 is smaller than 5, so we somehow need to move 1 to S. Well, why don't we just swap 5 and 1? After doing the swap, we need to grow S by 1. So I becomes 0, and that's it. Now S has one element. The length of B is still 0. Our current element is at I plus 1. We'll compare it to the next element. 10 is larger than 5, so we need to move 10 to B. I think you know what's going to happen now, that we are going to swap 10 with the last element before j, which is 9 in this case. After doing this, we are going to grow B by decrementing the index j. We compare 5 with 9. 9 is still larger than 5. We swap 9 with the element at j minus 1, grow B by decreasing j. We compare 5 with 0. 0 is smaller, so we have to move 0 to S by swapping it with 5. Well, that's it. There are no more elements to compare 5 with. And we can stop this iteration here. We have our lists S and B separated within the original list A without allocating any new memory. And 5 is at its rank, which is its correct position in the sorted list. At the end of this iteration, we are going to recursively call our algorithm on S and on B as we did previously. However, please note that in this case, there are 2 extra input arguments as well, which specify where should my sorting start and end. So this is going to be our algorithm. Remember, the crux of our algorithm is in these 4 lines, where you compare elements and swap their places to construct S and B and make sure that your P element goes to its correct position. Here are a couple of things which I think you should keep in mind. Firstly, rank implies sorting. If you know the ranks of elements in a list, then you essentially know the sorted list. And QuickSort is a rank-based algorithm, but it's not the only rank-based sorting algorithm. I have a hunch that you have seen a rank-based sorting algorithm before as well. The second point is that rank is easy to compute. Here is a short rank computation algorithm. It takes linear amount of time. This may look very simple and naive. Apart from being simple, this is also the most efficient rank computation algorithm. The third point, and I think the most important point, is that rank of every element in S is smaller than the rank of every element in B. I would say that whole of QuickSort is based on this fact, because what it means is that now you can treat S and B as separate sorting problems. And lastly, you can use some tricks to save space for S and B. Can you make a guess about how much space we have saved by the tricks that we implied in the last algorithm? Here is a hint. If you think that we saved linear amount of space, then you're probably wrong. Happy thinking!